Hello, my name is Justin. Today, we will be looking at protein-ligand interaction and how this can be studied using chromatography and UV-Vis spectroscopy. There are 20 basic amino acids, and proteins are made up of any number of these. The amino acids are held together by peptide bonds. Proteins fold into secondary structures called beta sheets and alpha helixes. They then further form tertiary structures. These tertiary structures allow for active sites to be on the outside of the protein. Here we see the protein hemoglobin and its active sites, the heme groups, which is the area that the ligand binds to. Ligands can be any molecule or atom that binds to the protein. These ligands bind with various strengths. Here we again have hemoglobin with two ligands that bind to it. As we can see, the ligands bind to the heme groups on the hemoglobin. The active site of this protein has different affinities for these two ligands based on the environment that it is in. This affinity for ligand-protein interaction is what this experiment will propose to test. Just like hemoglobin, serum albumin, which is also found in human blood, is a protein that has active sites that bind certain molecules. Using the pH indicator, phenyl red, we can study the protein-ligand affinity using UV-Vis spectroscopy and then applying Beer's law to find the concentration of phenyl red at various different pH levels. In this experiment, we will test two different ways that the affinity for protein-ligand interaction can be studied. One, oxygen and CO2 binding to hemoglobin, and two, phenyl red binding to serum albumin. To perform this experiment, we'll set up 6 different chromatography columns for each of the protein-ligand complexes that will be studied. Each column will be of varying pH levels. The pH should affect the amount of phenyl red that binds to the serum albumin and the amount of oxygen that binds to the hemoglobin. Once we have the solutions and run them through the column, each fraction will be studied using a Carey 60 UV-Vis spectrometer. The absorbency data will then be collected and recorded to be analyzed later on with Beer's law. For this lab, standard personal protective equipment, or PPE, will be used, including laboratory coats, goggles, pants, and closed-toed shoes. In addition, when Cephadril's G25 is being handled, a type N95 respirator will be worn, as stated by Sigma Aldrich chemical MSDS sheet. Also, because phenyl red is a stain, gloves will be worn at all times. Proper MSDS sheets and disposal containers will be on hand at all times. To keep costs down for this experiment, the use of Southeast Missouri State facilities and chemical instruments will be requested. Furthermore, the request for a grant shall be submitted to cover all chemical expenditures. Due to serum albumin's instability, the experiment shall last no longer than 3 days from the time the serum albumin is obtained. An alternative to buying the bovine serum albumin is to use human serum albumin. By obtaining donated blood and synthesizing serum albumin out of it would save the experiment $1,845. This will require the proper consent forms and the use of a phlebotomist with a proper blood draw area. Once the blood is acquired, it is to be centrifuged at 10,000 RPM for 3 minutes to pack all the cells at the bottom of the tube and leave only the serum albumin on the top to be decanted off. Once all lab work is completed and all data is collected, the data will be analyzed using Beer's law to determine the concentration of phenyl red for each pH level. These concentrations will then show the binding of phenyl red to the active sites of the serum albumin. This study would only be the first of many to study different protein ligand affinities in order to compile a database for these affinities. This would be effective in showing the specific pH level that certain drugs would work best in the body. Thank you to Dr. Adam Jacoby for his recommendations and guidance through this research project. And thank you for your time and your consideration.